Okay, I should be live, maybe. We'll see. It looks like I am. The latency should also be pretty low, so like the time lag between me saying something and you guys hearing it should be low, so I could respond to things fastish. Am I now? Uh, can someone pull up this? Send me the link of the slides from. The quality's really low. Yeah, that's because I set the latency to really low. Like, hold on. Oh fuck, it's like not readable. Okay. Um. Okay, but it's like really hard to read. Just kind of irritating. So. Oh, it's auto. Oh, there's 360p the highest. Yeah, okay, I'm gonna temporarily end the stream to increase the latency a little because the quality is really bad. Oh, can you go to 720p? Okay, no, never mind. I won't do that. It's not that bad. Okay. Well, I trust you guys. Um, Project, I think you're just at like really low. Yeah, I think you just have really low because it's auto quality. So like, if you have low, yeah, okay. Anyway, um, I'm gonna wait for a couple more people to roll in, and then uh, we're gonna go through the results. Is it? Well, I'm slightly sick right now, so like it's slightly different, but only slightly. It's still okay. Well, that's not good. Ugh. Okay, well, I need to pretend to keep some suspense here. Like, I'm not a jerk, so like, I'm not gonna be the kind of person who like spends 5 years on a name. And like, the really bad thing that I could do is do the problem review first and keep everyone in suspense for the results. But like, I was a contestant in math counts like 4 years ago. I remember that pain. I do not want to deal with it again. Like, God, that's like, please just give me results,
Wait,
right?
had a quiz you in math counts? That's concerning.
Like in math counts, it was like they're like it basically was like number 10 job, and then it's like takes so goddamn long.
Wait, no, in Texas they have like a whole like speech thing they do beforehand,
Yeah, it's so
and then
annoying.
they do a bunch of random shit. It's like, oh my god, please, bro. Like, then they're like, oh, we have this award and that award, and I'm like, bro, these are some irrelevant things. Like, oh, the math counts writing contest. I'm like,
Oh
oh
yeah,
my
there's
god.
like backtrack from the Texas thing.
Yeah, it's like please
Yeah,
shut the fuck up. Let me just do the
wait, and
awards.
I'm just like waiting there. I'm a coach now, and I'm just like, bruh.
Yeah, don't worry. Like when we start, which will be like very soon, because there's people now. Um, we're just gonna go through it pretty fast, honestly. Is it really? What the fuck? Um, That's not good. Whatever. Um, damn, that's not really great. Can someone change that? Because everyone has editor by link, so like make it view only. I don't need to edit this shit anyway.
I think it's view only now.
Okay, okay, good.
Oh my god.
Please don't do that. Okay, all right. So we're gonna start now. With the awards ceremony. Yeah, this is summer 2023. And by the way, you might notice that we used to call it just Matt. Now we're calling it Summer Matt. It's because there's winter and it's different. Okay, so some stats. We had 105 participants and no errors. Also, like, note the solve rates. We'll come back to it later because honestly, I don't want to keep you in too much suspense. Okay, the distinction is distinction 4 greater or equal 4. Yeah, I'm pretty sure it is.
Yes.
Yeah, we'll talk about P2. We'll talk about that. I promise. Yeah, this is greater or equal 4. For some reason, we also included everyone with in the top 10 in distinction as well. So like, yeah, if you're here, you may be in uh top 10. Okay. So number 10 is apparently a four-way tie between Fyodor, Isaac, Lin, and Rohan. Number 9 is Aditya. Number 7 is Adam and Selena G. 6 is Lurchen. 5 is Rohan. There's also a two-way tie for 3, Benny and Wilbert. Number 2 is Rui Lin. And number 1 is Alan Yuan, who is the only person to get a perfect score on the main rounds of mat out of every mat. Okay, so let's talk about some stuff, some stats. First of all, like, you might notice that this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and TB is 1, 2, 3. You might notice that out of all the P2s, number 2 is the lowest solve rate by a lot. Like, it's actually comparable to the 3s, which is kind of weird. Yeah, people submit at 30. Can you guys do us all a favor and just like submit at 29:55 or something? Like, cause at least that way, like, if you submit a minute earlier, right? Like, it'll break ties. Right
Yeah,
now,
all the guys are 30s.
right now it's like a disaster. Like, we're screwed. I'm not gonna lie. We're gonna have to figure something out. Yeah, please submit like at any time other than 30:00, because like the first two maps we got lucky. On winter we didn't really care about breaking ties, but like now I'm like, yeah, this is not actually gonna break ties. So we're gonna have to figure something out. And honestly, we might pull something out of our ass. Like we might look at submission times for earlier sets. We might look at other stuff, but like we'll discuss with the people, or we could like just split the prize somehow. Like we'll talk to the people who are tied, but it's gonna be a clusterfuck. Do milliseconds matter? I don't know if we store that, and I honestly don't know if that information is like reliable, because I think it's probably only reliable up to like the lowest sig fig or the best sig figs we have is probably up to seconds. Like, yeah, estimation problems like were what we were considering, but like they're fucking dog shit. I'm sorry, they're just bad. We'll figure something out that's like fairish. Estimation's bad. Like the whole point of math is like we cut out all the bullshit of bad math contests or like the bad parts of math contests like estimation or whatever. And like I kind of don't want to compromise on that. If people tie, I'm like whatever. Here it's a little bit of info. I don't actually care that much about top participants' experience. And like I know the people here are disproportionately the top participants, but whatever. Like I don't really care. Like as long as the problems are good and you guys enjoy solving the problems, like it's fine. I don't really care if it's too easy for top participants or whatever. Like I care more about the median. So whatever. If the tie-breaking format doesn't really break ties, that's a you problem. Like stop submitting at 30:00 if you have a problem with that. Okay. Uh, yeah. So yeah, this is a disaster. Pro tip: don't submit at 30-0. Okay, and that's the entire awards section of the ceremony. And we're gonna do some commentary about problems. Also, like we have official solutions, and yeah, it maybe will tell some of you that problem two's answer is not 36. We'll talk more about that later. But yeah, that's it for the results. Um, no, here's the problem with tiebreakers. You can never reliably break ties because if two people submit the exact same set of answers at the exact same time, then you're kind of screwed. There is no difference. Why 36? I think people just checked that's divisible by 4 and 9. It's like, yeah, that seems right. And they never checked for 7 or whatever. Like, tiebreakers, you can't actually distinguish between people with identical submissions, like identical performances. And that is really easy for people who have identical performances because a lot of people submit 30-00 and a lot of people, like, there's not that many problems. So, like, even Borda or whatever is not great. Anyway, let's just talk about the problems now. Uh, okay. So, Arush isn't here, the author of 3 problems. Oh yeah, I probably... No, you can't, because then you could vandalize. Yeah, I think, like, what we're gonna do is we're gonna edit... I'll talk more about tiebreakers later. But, like, in the summary, we're probably gonna, like, have the actual link say time matters, like, on the thing. Because the way Matt is designed is that strategy doesn't really matter. Because strategizing instead of solving problems is kind of annoying. It's kind of cringe. Um,
Yeah, so this is like a conundrum that's like bad and, part of math. It's just solving a problem.
yeah, tiebreakers are hard to design. Okay, anyway. I'll discuss this problem. So, someone already posted this in the thread, but there is this really, really uncanny resemblance to 2015. God. AMC. This is so laggy. For no reason. AMC 8, number 25. And that problem is basically like, here you have this square, and you want to construct this guy, right? And you want to find the area of this guy, basically. And yeah, this is similar. So the way you do this is you plop this, plop this, plop this, plop this, da, 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 da. And okay. So if you do BH halves, yeah, you're gonna kind of notice that. Let's look at each of these 5 squares and look at like the total of these areas, like these given areas, in terms of how many squares they sum up to. Like, notice that half of this square is filled in. Like, you can just show this by BH halves. I won't go over the details. But half of these 4 outer squares is filled in, and the whole inner square is filled in. So you have like 4 times a half. Wow, whatever. I'll just use a text box. 4 times 1/2 plus 1 equals 3. So you have 3 squares out of these 5 squares of area filled in. And these 3 squares sum up to 11 plus 4 plus 4 plus 4 plus 4, which is 27. So 27, so 11 plus 4 times 4 is 27, which is equal to 3/5 of the area. Which implies that the area is something. It's 45. Yeah, so the answer to this one's 45. Who's covering number 2?
Oh, I think I am.
All right.
Sure. Okay, so number 2. Anyone have any lore to talk about this one? I think we all try to solve it some way. I think for Chief, who's a host, and um, we had a more um, algorithmic approach to this problem. So that means kind of like using logic and then listing out the possibilities, and that's probably like the way to go. But I understand that a lot of you may have just because the premonition in math contests is that a lot of these problems that try to guess this common divisor thing are just kind of like asking you to like test, heck, even like multiple choice questions. Like the answer choices are like 9, 18, 27, and you just wanted to test them. But and what you do is like when you guess the answer and then you just confirm it's correct. Like that seems like the main um, structure by which you're like told to try these problems in. Now I'm not looking at the chat right now, but um, um, yeah. Anyways, so this problem, what you're supposed to do is you start with A and B, which are two different non-zero digits. Hope you can see that. But because Jerry has the two digits that are distinct, so at least two of them have to be A, B. You could have C. Doesn't really matter. But what's important is A and B, and technically A and B could be at the end of the number. So like you could have um, four four digits that you don't know about, and then you have A and B, or you could have the other four digits in the same order as previously, but with B and A. So, sorry. The thing with text boxes on Jamboard is that you actually have to click down to like show stuff. But yeah. Anyways, these two numbers only differ by like 9 times B minus A. So that actually means something. So if n is to divide both these numbers, then you would have n dividing the difference of the two numbers. So the difference of the two numbers is quite small. So right away you get that n is just not that large. Difference specifically is 9 times b minus a. I'm just going to assume that b is more than a. So that actually leaves you with a finite number of possibilities. Specifically, this can't be anything larger than 72 because B and A have a maximum difference of 8. So I was actually interested when I tested out this problem by Colin. Colin is an awesome problem writer right away. So when I tested out this problem, I was kind of like, I'm actually gonna test all the possibilities just to see what's happening because I just didn't have that much interest in actually solving the problem. So I was like, gonna test what happens when b minus a is like 8, 7, 6, 5, 4. Keep on going down there. So obviously, I found just like you guys that 4 would work. I'm not going to provide too many examples there. I think even if you have 8 and 4, 3 8s and 3 4s, for example, that's probably going to work. But anyways, if you look at 9 times b minus a, what you want to do logically, right, is you're supposed to check from the top. So you're supposed to check from 72 to 63 to 54 to 45, and then to 36, and so on. Now, 72 is not going to work just because it requires 9s and 1s. And if you think about 9s and 1s, and you want it to be divisible by 9, and you have at least one of each 9 and 1, then you're not going to be able to produce a number that's divisible by 9. So if you have exclusively 9s and 1s, which is this case right here, that's not good for you. So you're going to have to try this. And if you try this, you'll have either 8 and 1 or 9 and 2. Obviously, you could have more digits, but that would just make n smaller, right? Because that would be more restrictions on n. More obviously, 8 just doesn't divide. 9, yeah. Yeah, I always, when I look at the problem, I always miss that condition about evens and odds. Yeah. I'm kind of trolling here, but detracting from that situation, 8 and 1, this is solid, right? 63 is odd, so you're just trying to get 7 and 9 to like divide. This is actually the problem with 9 and 1, since this time it's actually an odd number, so you can't use the odd and even argument with 72, but you could use the multiples of 9 argument here, that this one doesn't work. And then 8 and 1, well, that's actually works out perfect for us because 8 plus 1 is 9, so if we have 3 copies of each, so 3 8s and 3 1s, then now you can check, and this is the extra nice part, is that you can check that if you have some combinations of 8s and 1s, like this one, then what happens is you can like basically remove the factors of 7, so that you get just a line of 1s, 6 of them, and this is magically divisible by 7. And there are a few ways to find this out, but what Cullen suggested was to use Fermat's little theorem. So like 9 times this is going to be 10 to the 6 minus 1. So basically using mods, any non-zero factor to the p minus 1 is congruent to 1 mod p. So this thing would be divisible by 7. So that's a nice finish to the problem. And you can see that 63 is actually a valid answer. And now I obviously found something pretty interesting with testing 54 and 45, but that's beside the point. Yeah. Okay.
I'm doing problem 3. All right. So I guess when you read this problem, you see that it's asking you to like find the maximum possible area of ABCD, and this implies that ABCD is not fixed. So you kind of like want to figure out what the structure of ABCD is. First, let me quickly draw a diagram. That's not a good thing. One sec. So I guess I guess one motivation is that like you only have 4 degrees of freedom. So what that means is like if you're given any random quadrilateral ABCD, P is perfectly determined, and quadrilateral is like there's 5 constants you need to be able to like perfectly determine them. But in this problem, you're just given 4. You have like PA equals PB equals 3, PC equals PZD equals 3 root 11, and you have these 2 angle conditions. So this means that there's like 1 degree of freedom, and this could like motivate thinking of this pivot idea. Another degree of freedom, another like motivating idea to solve the problem is you're pretty much just given information about 2 different triangles, and these are the 2 different triangles. One sec. So pretty much all of your information in the problem is just about like triangle PAD and triangle PBC. So you can kind of think of them as like separate entities. You have 2 sides of these 2 triangles, and then you have their angles in terms of each other. So sort of triangles APB and triangles PDC don't matter. So you can just kind of like try use triangles PAD and triangles PBC to try to do something nice. And one way to like utilize the angle conditions nicely and use the fact that you have triangles PAD and PBC determined is construct a point like E on PA such that PA equals PB equals PE. Now, the crux here is that by angle tracing, you can figure out that angle DPE is equal to angle CPB, and since like they share the same angle and they have the same sides, PD equals PC and PE equals PB, you know that these two triangles are similar, are congruent. So what that means now is that, like, first of all, you have angle PDA plus angle PCB is equal to 30 degrees. So angle PDA plus angle PDE is equal to 30 degrees. So angle ADE, let me draw it again really quickly. Angle ADE over here is equal to 30 degrees. Now you know that the length of this side is 6. And you know that the median, which is PD, has length 3 root 11. So by using law of cosines, you can figure out like the constants in triangle AED and just figure out the area of this triangle. And now to finish, to find the area of ABCD, you can notice that, like, if you let this angle be theta, this angle is going to be 180 minus theta, and then the idea is that both triangles APB and DPC, both of their areas are maximized when theta is equal to 90 degrees. So you can just set it equal to 90 degrees, find like the area of both of these right triangles, and then add the area of ADE to that, and then you finish. I think the answer ended up being 72. I recall seeing that some people are getting 74 by like assuming P is the intersection of the diagonals. This doesn't work because P cannot be the intersection of the diagonals. Like APD is not equal to BPC, so therefore it's not the intersection of the diagonals. And yeah, the answer is 15 squared 3 plus 54. The 54 comes from triangles APB and CPD, and then the 15 squared 3 is from triangle ADE.
Awesome. Yeah, so the idea is like APD plus BPC is fixed, and that actually was our old um, extraction. But yeah, then we added this like idea about 90 degrees. Like,
Something is actually like another funny solution is you could kind of like smush APD and BPC together, and then you would find this the triangle on the right or something.
alright. Is Jerry here? Who's taking over for
No,
Jerry?
I was gonna go over this
Okay, awesome. Alright, go for it.
Okay, so this one is essentially just a clever perspective. The first thing you need to realize is that fundamentally the order you fold these creases doesn't actually matter. Sorry, one sec. And then once you realize that, then you can just choose to fold one of the edges first, and then there's only one way to actually fold the rest of the edges. So, essentially, out of all 32 ways to fold each of these 5 edges, you can, let's say we're just choosing the edge between the 1 and the 2. In that case, there's 2 ways to fold that edge, and after you fold that edge, there's only one way to fold the rest of the edges. You actually end up creating a cube. And so the answer actually ends up being pretty elegant like that. There was this like solution originally proposed I won't go over, but it made it kind of, the funny thing is it just made it kind of confusing internally because it was hard to understand why the proposed was wrong. And it kind of had to do with like the orientation actually means. So like was vaguely about like checking which faces were on top or bottom. You end up folding the cube into a cube. And yeah, it ended up that like fixing the orientation in a certain way caused the solution to be wrong. But yeah.
Alright, next one's mine. This is my only problem on the test, and I actually think it might be surprising that this is my problem. Or maybe it's not. I don't actually know. But anyway, so this problem, the idea is like, let's just explicitly represent P. P is, I don't know. There's just some AI x to I. I'm being super vague here because it doesn't actually matter what AI or xi really are, like, except for the linear term and the constant. So we take P of 11 mod 121. You know what, let's just actually write mod 121. Also, this is wrong. It should be AI x to the I. Linear comb poly, not lin comb. I mean the linear and the constant terms. Yeah, okay. So if you take this mod 121, you get 11x plus, sorry, you get 11a1 plus a0. Like mod 121. Because the rest of the stuff is just divisible by 121 and it just disappears and it just dies. P of 13 mod 136 does something similar. Or 169, sorry. It's just like 13a1 plus a naught. And the general idea is like, we're going to throw away some information. And this is actually kind of scary because like, we're not just transforming information, we're actively deciding which parts of information don't matter, which is what makes this a little bit scary. But like, the way I constructed it was backwards. So it felt really easy to do this for me, even though like I intellectually understood that this problem was not trivial. Anyway, so the idea is we're actually just going to look at this thing like mod 11 instead. So, like, to say the remainder is A and to say it's congruent to A mod 11 are not, or mod 121, are not quite the same. But, like, we can say that A naught is congruent to A mod 11, right? Like, this is congruent to A mod 121. So if you just take mod 11, you get A naught is congruent to 1 mod 11. Similarly, A naught is congruent to 2A mod 13. And I'm not going to do the details, but essentially what you can do is, this is like Chinese remainder theoremable. And basically, like, you can either guess or systematically do this, but you will eventually find that these two together imply that A naught is congruent to 67A mod 143. And now this is a little suspicious, right? Because you have this 143 and this mod 143. So like, essentially the way I was thinking was like, the way I constructed this problem, and it's relevant to the solution because it's literally how you solve it. It's like, okay, let me make this thing. Let me somehow like force, like, I think originally this was 11 and 13. Before I thought, okay, how can I disguise this and make this twist a little better, right? And anyway, so the idea is you throw away this information because you don't need it, and now you have this 143 and 143. And the big idea is, why don't we take a look at 143, P of 143, mod 143, right? And like the linear term and everything after it just disappears, like, because x to the any power except for 0 is divisible by 143 because x is 143. So this is just congruent to, and then I'm abusing notation here, but this is congruent to A naught. But guess what? We also know it's congruent to 1407 because we know what P of 143 is. P of 143 is obviously congruent to P of 143 mod 143. So you have this as this 67A. And essentially, you can like do some relative prime checking, and you're gonna essentially get that A naught is congruent to 1407 over 67 mod 143. But this is equal 21. How do I get 67A? Yeah, there's a lot of ways to do it. There's an algorithmic approach. Yeah, it's not A. Yeah, this is A. You're right. Whoever erased that. There are a lot of ways to get A naught, but essentially what you can do is just keep adding. You take this, you start here, and you keep adding multiples of 11, right? Like this is congruent to 12A. A naught is congruent to A is congruent to 12A. And you see that 12A is not congruent to 2A mod 13. Oh no. And then you go to 23A. Oh no, this doesn't work either. And you're like, you can be sure. Because 11 and 13 are relatively prime, if you keep repeating this process, you'll eventually get to something which is congruent to 2A mod 13. Like if 67A is congruent to 2A mod 13. Yeah, I can like privately message you after stream about the specific details, because this is sort of a like this is part of the NT literature, and it's not quite as simple as I'm making it out to be, and I'm basically like hand waving some stuff here, some details, but like essentially you can, with some wishful thinking, be like, huh, okay, I wonder what value would what multiple of A would simultaneously satisfy these two equations. Like satisfy one and blindly add stuff until you satisfy both. That's basically how it works. Okay, and now this is Aaron's problem.
Oh, I actually wanted to talk about how Dennis's problem had those like we had to have a roosh find a polynomial that work to this, and that was an interesting task.
Oh yeah, that's worth discussing. Like we had this solution. It's like, wow, if such a P exists, then it has this thing. But then we're like, wait, does such a P actually exist? And we're like, great question. And I was like, I'm pretty sure it does. Let's actually just programmatically check that it does. And someone found the really cursed polynomial. It's somewhere. It's like really ugly.
It's linear though. It's linear.
It's linear, yeah. Like I was pretty sure you could construct a linear polynomial, maybe. There's like a lot of stuff you can research with this problem. I think it's pretty interesting. I will type it out. Yeah, this is a polynomial. It's 82x minus this. Okay, now I'll hand it off.
Okay, so this problem looks long, but it actually is pretty short for problem standards. There are a lot more longer problems than this, but hopefully I didn't scare y'all. I mean, the first condition is just each cell contains one number, so hopefully that's okay. So basically, what happens is what happened during problem construction for this problem was that I basically this is my problem, by the way. I basically drew a couple of arrows, and then I drew a couple of arrows here, I guess. And then I was like, wouldn't it be nice if there was a non-contradictory, like a flow set. So like in this case, you would run into the problem of like let's see. Yeah. So if you flow, okay, by the way, I'm gonna give you a disclaimer here. This arrow thing, I actually disagree with this. This is a huge debate. I'm just gonna say it's a decrease. But um you guys can vote in the chat whether you thought decrease or increase was better, but I like decrease, so guess I'm based or something. Yeah, so basically this represents like the flow of stuff. So this square is supposed to be greater than or equal to this square in number because well, this is less than this. So basically you can form a cycle here, right? Which is bad. Because if you have like 4 numbers where each one is like successfully greater than the other one, then that's like a loop, right? So in this case, your loop would kill the possibility of you arranging the 25 positive integers. So that is pretty poor. So this question is basically asking how many of these side configurations here and here. So out of 1024 2 to the 10th side configurations, how many of them result in something that avoids the loop? And basically, if you actually get to that step, you're very close to solving the problem. But it's actually a little bit harder to show that if you do not have the loop, so when you don't have the loop, that you can actually file in all the positive integers, and that's also a fun subproblem. But essentially, what it means is that if you have rows of like alternating sign and you have certain columns of alternating sign, then if you have enough rows that alternate in sign and enough columns that alternate in sign and you intersect them, then you're going to get you're guaranteed to get a loop. So so in this case, this is like a 3x2 grid. Oh, pardon that. So just pretend this is a line, and so you get this loop, right? I'm gonna draw it right now. So this will be greater than this because I said decrease. So this is going to decrease, and then we're going to decrease again, and then followed by this decrease, and followed by this decrease. So it turns out that whenever you have any 3x2 set, it's problematic, and it will have a loop because these 3 things cause a set of 4 contiguous squares to contain a loop. So either these 4 contiguous squares or the bottom 4 contiguous squares will have a loop in it, no matter what exactly these signs are. As long as they're alternating, this will become a problem. So basically, you simplified the problem into having no loops, and then having no loops means precisely that you want to avoid 2 arrow changes and 1 arrow change here. So basically, that leaves 2 cases, and the first case is where all of the arrows on either the rows or the columns point the same way, and the other case is when there is exactly 1 alternating sign. So I'm gonna like give you a snippet of how to observe and confirm both work or something. So in this case, all these 5 things are pointing this way, which means that this is the largest row, and then successively you can see that there are the numbers in the rows get smaller and smaller. So on the top, you would have to put 1 and 5. Oh, well, not 1. not you would have to put, but what I recommend is constructing this just to show you like that it can be done without a loop. So obviously here there is no loop because there is no alternating signs in any of the columns. So you have 1 through 5 all on the first row, then 6 through 10 on the second row. And if you have 1 through 5, this is probably drawn incorrectly, but just ignore that. So if you have 1 through 5 in the first row, then you can just follow the signs in the row. And if you have 6 through 10, you can follow the signs in that row. And same thing all the way to here. So obviously, if you have a fully uniform row or column, then it will work. So you can do a little bit of principal inclusion exclusion here, and you'll get 124. And the other case is that you have a specific turning point when the arrows turn in a certain direction. So in this row of column arrows, eventually the up arrows turn to down arrows, and in this set of row arrows, eventually the rightward arrows turn into leftward arrows. So basically, that's the other case you have to consider, and you have to be a little bit careful here, because you could either accidentally form a massive loop, or you could form a successful solution. So what I mean by that is, if you have, okay, let's just say we have, my drawing speed is pretty slow right now, but if you have this, and then you pull this off, so as you can see here, this is where the arrows have changed from rightward to leftward, and down here 4 leftward arrows, and here you have 3 upward arrows followed by 2 downward arrows. And this particular solution is unfortunately going to cause a problem. So what I mean by that is you have this region and this region, and what essentially happens is that you have a circulating flow. So this creates a loop, which is poor. What I mean by that is if you look at the 4 squares next to the intersection of these things, they form a loop. So this thing, this thing, this thing, and this thing form a loop. So if you wanted to correct this, you would have to find the correct parity of the orientation. So in fact, if each of these row arrows were reversed, we would have a successful solution. And by that, I mean you would have, let's see, yeah, this way, this way, this way, this way, and this way. So in this case, you have a similar thing, except you have what someone in the thread and what I call a low zone and a high zone. So when I first made this problem, I made a YouTube video on this. I don't know why, but you have a low zone where basically all the arrows form like the minimum. So like this column arrow is pointing. I'm going to use this. So this column arrow is pointing downwards, and this row arrow is pointing rightwards, and they intersect in this box right here. And this box is actually the minimum. So you would choose your small numbers to put here, specifically 8 of them, and you would pick your 3 other small numbers here. So 1 through 11, you could say that 1 through 8 will go here, and 9 through 11 will go here. And the high numbers, 2 of them, and then 12 of them, you could put them here and here. So in this case, in each uniform box, you could tile them correctly, and the boxes wouldn't interfere with each other. So you could actually count that. And the number of cases where this is possible, so either low, high, low, or high, low, low, high, is going to be 32. So if you add them up, you get the answer. Any lore? I don't have much more lore.
I just want to say, like, this problem has been in, like, we wanted to put this on the mat for a really long time, and we finally found the opportune moment on this mat. Like, this problem is pretty old.
I also want to mention that like a long time ago, we thought this problem was very close to like Amy 15, like very impossible difficulty, and then we gave it to some test solvers, and I think they were like, nope, this is not that. And I think ultimately they were correct. It was not that bad. It was still bad, but it was not that bad.
It's doable. It's in the realm of possibility. Like it's tipping its little toes in the realm of doable. So yeah, this is a really good one. I think we like was this proposed after or before the first mat? I think after.
I think
Wait,
I
I'm not even
proposed it,
convinced.
like
This thing is.
June 2021. Well,
Wait, yeah, this thing
I was
is
thinking about during like
long time.
I was
It
thinking
might.
about this during certain camp, but
I'm sure we could check, but like this is really old. Like we didn't use this on mat 2 because we wanted to make it easier because we didn't have winter. But now we had winter this year. We're like, okay, now we can now we can kind of go off the rails on summer. And we're like, okay, we shouldn't go off the rails on 1, 2, 5 or 4, 5 or sorry, yeah, 1, 2, 4, 5, 7, 8. But like the problem threes, we're like, yeah, we're going off the rails, and we kind of went off the rails.
yeah, the winter problems also have some lords in them, so yeah, all the problems
Yeah,
have a little bit of lore.
I like the winter problems a lot. Okay, who's covering this
Yeah.
one?
I can do
I
the
can
next.
do it. Oh, wait. I can just talk about all of set 3 because it's fine. Is that fine? Okay. So this problem is sort of. I would like to say that I guess it challenges you to work backwards in the sense that like you can do like obviously this is not going to be like a super like there's not going to be any angle chasing in this problem. Like that's pretty obvious. I guess the first important observation is this like is this sort of proving that this thing is 15. I don't know why we resized the shit. Is my internet going out? Oh my god! The great state of Texas strikes again.
Yeah,
Wait,
nothing's being drawn on the thing. I don't know
wait.
if this.
Also, there was originally some stuff on there, but I guess that's gone. This is fine. Okay, so the first step is like there's this like kind of very like ancient like geometry lore thing that's like this thing is 15, and you can prove this by showing that like okay, this like if x is this sort of midpoint tangent thing, then because ax squared is equal to big R squared minus small r squared, and that like pi times this is equal to this thing is equal to the area, like the difference of the areas between the circle and the outer circle and the inner circle. So this thing is just going to be 225 pi. So that's how you get that this ax is 15. And then this little vertical thing being 3 means that this thing is 12, right? So again, as I said, working backwards because you're not going to be able to set the inner radius to r and then like find your way to 13 and then just like solve for r. This is going to kill you. Instead, you sort of have to work backwards. So this 13 here, and then you have this 12, and you're like, wow, that's a triangle. So you have this 5. And now I have completely cluttered the diagram beyond. Anyway, um, there's a lot of ways to proceed from here. I think essentially anything will work, but the cleanest way is power of a point. So this intersection is like, I don't know, E or something. Then like AE times CE equals BE times DE. These are known lengths. These are 12 and 18. And these are findable in terms of your radius, right? These are like BE is 5 and DE is like 2R plus 5 or something like this, or something similar enough. Yeah, that's what it is. And so if you just like, yikes, wait, did I break something? No, it's fine. It's fine. Yes. Okay. And then if you just like solve this out, you get r equals 191 over 10, which gives you the answer of 201. Is there
This
anything
problem
else
is
that?
this
Sorry?
problem is really easy to like solve sussly, suspiciously.
I mean, I think that there's a lot of ways to make this harder for yourself. Like, I think this is not chord bashable, at least like not easily. I would love to see one, I guess.
I think it's quite easy actually.
But really, but I think the I don't know. I'm not convinced. But in any case, I think that it's it's a very instructive problem in that it sort of makes because the answer is very ugly. This probably suggests that like there's not like a super like not every like ordering of doing the like not every way of doing the problem will result in an equally nice solution. Um, because of how like you could, again, as I said, like set the radius as a variable, try to solve for everything in terms of r, and then get some function of r equals 13 and just like see what happens. I guarantee you this function of r will be very ugly. And you can probably do it, but it'll probably give you like this is non-trivial, right? So it's just sort of making the correct observations in the correct order to make the solution efficient.
I'd like to mention, like, originally the extensions of like extending A like all the way to AC and like B all the way to D, not originally there. So all you had was the right triangle. And so maybe that was less conducive to the power of point originally. Yeah, I feel like adding the chords in made it more conducive.
This is true. I also think that there's definitely non-PowerPoint ways to do the final step that are not that bad because at this in the final state you do already know that like R, the big R is like, yeah, you know some pretty like important facts about the big R already. You can find the big R in terms of the small r because like you know that like this thing is going to be like small r plus 5 and this thing is 3, so you can find big R as some like function of small r, and then you can do two things. There's like two equations or something, but yeah, PowerPoint is still very clean.
I mean, I think a very obvious way is like you have pi r squared minus r squared is 225 pi, right? So like you can trivially find big R from little r. It's very easy.
Well, no, I'm saying no. There's two ways to do it now because
Oh
now you have
yeah.
this 3 and 5 thing, and that gives you another equation. And then we take the difference between those two equations. I think you ultimately get the same equation actually because of it's basically the same argument behind like linearity of PowerPoint or something like that. It's pretty. It ends up being pretty clean. But
Okay.
yeah. Okay. Is there anything else?
Next problem.
Okay. Yeah. Okay. So this is my creation. I guess I want to briefly talk about how I came up with this. If y'all don't know, there's this fact that like this thing and like how do I phrase this effectively? This angle. These are just things that I remember for some reason. This angle plus this angle is 45. Like when you do something like this is like a really bad diagram, but something like if you label them like this, the sum of this angle plus the sum of this angle is very clearly 45 for reasons. And I was sort of trying to fit them in the same triangle, right? So I came up with this triangle, which had a 135-degree angle in it, because of, again, pretty similar reasons. And so I was like, wait, that's kind of cool. What can I do with this? And I wanted to find more general things of this form. So the better question is like, when is this angle going to be 135? And there is a nice way to geometrically do this if you're really like smart enough, but I didn't do this. Instead, you just think, okay, tangent theta is equal to tangent theta 1 plus tangent theta 2. And then that's like, there's some work to be done here, but essentially you get something like x plus y equals 1 minus xy or xy minus 1 or something similar. When you actually like use the tangent angle addition formula. And so this is where the key claim in this problem comes about, if I can just erase everything in a reasonable way. Because the xy, of course, reminds us of power of a point. And so essentially I'm just gonna take a circle. Take this circle and let's draw a quadrilateral with this 45-degree angle thing, right? I mean, okay, this diagram is very, very much not to scale, but essentially, B, C, D. This being 45 means that if this intersection is x, then like bx minus dx equals ax plus cx, or alternatively just AC. Again, you can prove this with tangent angle addition. There's a nice way to do this by adding in the orthocenter x, the circumcenter O, the midpoint M, and doing some magic. But in any case, this is sort of the key claim, because once we have this, then it's just a length chase. Essentially, because of sort of how the similar triangles from PowerPoint come about, we know that bx is like 5/3 of ax, and or cx rather, and ax is 5/3 of dx. Again, this just comes from the same similar triangles that you use to prove PowerPoint. And then by applying this, you find that this is like a 4-to-1 ratio, like bx over ax is 4-to-1 or something like this, which allows you to just directly solve for bx, ax, cx, and dx, which allow you to find the area rather readily. Yeah, so that's how you get the answer. The answer is like something like, I don't know, 21 over 2 equals, gives you the answer 23, or 23 over 2 equals 25. I forgot. Well,
It should be
but
23
yeah,
over
that,
22.
yeah. This is also what I remember. Yeah, it's yeah. Any other notes? I think this problem is like, again, I think my problems in this exam were pretty indicative of my current, I guess, writing style. The problems are not super like, I don't know. I'm not of the opinion that this problem is super clean, especially if you don't like really sort of boil it down to this kind of thing. And in general, I think that my problems tend to be pretty like almost like Amy problems, in the sense that like there's a lot of ways to do it, but the problem itself, like but it's not super conducive to the problem itself being nice. I do like the main idea, but I think ultimately I suspect a lot of y'all try to do something bash adjacent on it. Yeah. Sorry. Am I like spending too much time on these things? Okay. Yeah, we can go to the next one. Okay, this is an interesting choice for a P9, because I mean, personally, again, I think the problem is really good. I think when I asked the other members of Mac whether it was good, they were like, yeah, the main idea of this problem is very elegant. But I have no idea how much people actually liked it. I also do know for a fact that, like, if you look at the solve rates, that this problem was not that difficult. It was actually tied with P3 for being the easiest third in a set. But I don't know. I still think the idea is really good. I just, again, I have no idea what y'all did to do it. So when I was visualizing this problem, it was like, I mentioned this in some AOPS post on the same thread, but essentially I was visualizing this geometrically, right? Let's say basically what we're going to make is we're going to make this sort of like 3D times table mod 29, right? And like, this is the way that I was thinking about it. There's a more reasonable set formulation that is in the official solution, which will be coming out soon. I just want to sort of explain my thought process. So like, let's say we label each of these like 1, 2 to 28, and like similarly for these, right? So basically the problem asks you to sort of find the distribution of the residues mod 29 in this smaller 26 by 26 by 26 box, right? So naturally we're sort of asked the question like, okay, like what's in this box, right? This is like a very like, this is not like sort of well distributed, and in fact like finding like what happens at like the edges or whatever, those are kind of irrelevant considerations when we're sort of looking at this sub box. So instead we sort of use a sort of PIE style argument, right? So we sort of try to turn this small box into sort of, we subtract pieces from the big box to sort of get to the small box. So we subtract these sort of large, like plane-like pieces, these 2 by 28 by 28 pieces first. So we take the big box. I'm just going to label this like 28 or something. And then we subtract 3 like 2 by 28 by 28 boxes, right? And then that gives us we've over subtracted a lot, but we can add back these 3 like 2 by 28 by 2 rods and then subtract a 2 by 2 by 2 cube, right? And this gives us our 26 by 26 by 26 cube. And these individual pieces are all equidistributed, i.e. like there's an equal amount of like 1, 2, 3, 4 all the way through 28 in these because they have one side length which is of size 28. So everything else will just sort of be equally distributed because if you know anything about sort of like whatever like reduced or complete residue systems, when you take a reduced residue system and multiply it by another number that's not like literally 0, you will get another sort of like reduced or like reduced residue system, i.e. like spanning all of the residues mod 29 that are not 0 because 0 is bad and makes us sad. This is why 29 being prime is important at all. So these pieces are equidistributed. So we know that this plus this will also be equidistributed, i.e. like this will be equidistributed. So now we only just have like, I guess, like a few concerns remaining. The concerns are like, okay, what are our remainders that are sort of special, right? And the answer sort of lies within this smaller term because this is like -1, -2 cubed, and these are the ones that have deficit, right? So what we're missing is this entire thing has size 26 cubed plus 2 cubed. So for each of the residues, because they're equidistributed, i.e. like there's equal amount of each residue, we know there's 26 cubed plus 2 cubed over 28 for each residue, right? Now we're sort of subtracting these 8 residues out. So we know that we're missing 1, -1. We're missing 3 -2s, 3 -4s, and 1 -8. So these are clearly the ones with the biggest deficit, which correspond to 27 and 25 respectively. So that gives you your n of like 675 or something, and the smallest value in the sequence is just this entire thing, this expression -3, which miraculously happens to be 625. I have no idea why this is true, but it is. So when you add these two, you get the answer of 1300. Yeah, again, there is a more well-written set formulation of this like very spatial idea. I think it's just because naturally I like to process things like this with geometry, even if realistically they should not be processed like this. But yeah, I hope someone enjoyed this problem. I definitely had a fun time thinking about it, I guess. But I also, again, same thing as I said for the previous problem, it sort of feels very AV to me. I feel like something about this feels very again, the problem itself may have some elegant underlying idea, but it's very easy to get lost in the details and sort of become saddened by pieces of the problem that I did not intend. In particular, it took a lot of time to turn the idea, which is just sort of like this PIE style, like boiling it down to these two pieces at the bottom. These again, I realize I'm drawing a lot. Maybe I should change colors or something. These like pieces at the bottom were like this idea had persisted in my head for a long time, but it took a long time for it to turn into this problem because there are a lot of ways you can state this, some of which are more computationally intensive than others. And we boiled down it to these two pieces M and N that sort of force you to understand what is going on in the cube very completely. And of course, the sequence is sort of an accessory to that. Okay. Anything else y'all want to point out about this problem, or am I just done? Oh yeah, it was like something like ACE minus BD. How many sets of A, B, C, D between 0 and 9?
5-digit numbers, yeah.
Such that this is like 0. This expression is 0 mod 13. The issue with this formulation is just that the answer is way too ugly, I think. I actually think this is fine, but I mean, realistically, it's just sad. Yeah, I think it was attractive to us because the statement was very nice. Like A, B, C, D, E are literally just digits, and we just want to know like what happens if how many times this thing is 0 mod 13. Like this is a very intuitive question to ask, but the process of actually resolving this question is actually it is easier for you to be sort of quote unquote stupid about it, I guess, and that is undesirable. We want you to try to actually find the nice structure at the heart of the problem. So this is why it's formulated in this way, which is a little more complicated.
The other formulation that I liked that you suggested was the expected value one, but that ultimately resulted in the same issues.
The number was super ugly. Yeah, it would have been really funny if I had back-to-back expected value problems on the maths. It does, and one thing I do appreciate, like aesthetically, about this problem is that it does kind of look like a final boss problem, which is good. Even though, like, I don't think it's final boss problem difficulty. It has final boss problem aesthetics, I think, at some level. So this is good. I don't know. Yeah. Yeah.
Yeah,
Well,
I
I
think
think like
was done pretty well this time around. But that's
I think this is a lot easier than Mat 1. Maybe not a lot. Like, Mat 1 P9 was pretty easy, to be fair. Like, honestly.
Yeah. It was not really non-standard. Well, I mean, I guess it was non-standard since the idea is unique, but there's so many ways to do it, and it's like it's a very it does feel like the techniques that you would use are still kind of combinatorics 101 at some level.
Yeah, like, you can just try to solve the problem and you will succeed. Like, that's what I feel about that one. But, like, that's, like,
Yeah.
pretty good. Because, like, not being able to solve problems is bad. Like, problems should be solvable.
This is so
Anyway,
true. Okay, I think we're done with this, right?
yeah.
I just wanted to say like about the final boss problem aesthetic. I also like if the final boss is something that like really simple, like that famous like Putnam tetrahedron problem that and it just like sounds really simple, but like no one can solve it. I don't know. But anyways, so this is the problem I proposed to this test, and it's not like it's not that difficult, but I guess I'll go over how I made it as well. So like the way um I wrote this problem is like I just wanted to combine two math things that like aren't usually combined, and it's like I don't know if it's actually like it's just it's not a rigorous way to think about it, but it's just like um kind of like the way I wrote this problem. So I was thinking about like a function, and then it like takes in like a set, and then like outputs another set. Um, and I just want to do something with this. And I think when I like before I wrote this problem, I watched like DJ Mathman's like a video on writing problems or something, like some point before, maybe like a month before or something. Whereas like if you have a problem about like a function or a polynomial or something, then like you can ask about the roots of that thing. So like you can ask about the roots of a function or roots of a polynomial, and like those sometimes lead to good questions. So I'm like, okay, so if you had a function where it was taking in a set and then outputting a set, like what would you consider the root of a set? And like obviously the natural thing is if it leads to the empty set. So I was like, okay, this is a pretty good start. So like, what's a function that would be interesting to define on a set that would end up leading to an empty set? And that's when I came up with this process that occurs here. So naturally, like the first kind of set you'd apply this function to is, well, I just applied it to like 1, 2, and so on. But the pesky thing about 2, and yeah, 2 and 1 basically, is that they're like divisors of a lot of the rest of the numbers, which kind of interferes with this process a lot. So that was the one thing about this problem that I wish 1 and 2 like didn't exist, so that this would be like like a nice statement. But yeah, alas, I had to settle for 3, 4, 5, up to 10. But now to actually solve the problem. So the idea is most of the divisors in these out of these numbers are like independent. So for example, like 5, there's only one number that 5 divides in this, and that's 10. And then we have like 4, 8, and then there is, now the nice thing about this problem is it's not completely trivial. So like 3 divides both 6 and 9. So yeah, the idea is you basically you multiply, like you can choose to include any one of these sets, but then you subtract off 4 because you can't include both 3, 6 and 3, 9 at the same time. Because for example, if you had 3, 6 and 9 in your subset, then when you remove it, you'd remove, like when you remove 9, you'd remove 3 and 9, and then you'd be left with just 6, so you'd never be able to remove 6. So then you're left with 12, and then this was like what I was debating, is whether to include this non-empty or not. On one hand, it causes the problem to be like pretty sillyable if you get 12, but also I feel like this problem is better defined if the input set is non-empty. So yeah, I just went with non-empty and I bolded it to like hopefully save people from sillying, but I can still see people missing the non-empty. But yeah, anyway, the answer is 12 minus 1, so you get 11.
Alright, next up is two of Arusha's problems. He basically wrote the majority of this tiebreaker, and I'll be covering this one. So yeah, this is a really, really nice problem because there's like a lot of ways to do it. And I'm not gonna try and draw the correct diagram because like it's just gonna be a disaster if I try to draw this. Alright, so I'm just gonna copy this here from the solution booklet. Alright. So you kind of extend the triangle like this, and this kind of looks right, but it is right. And alright, so the idea is we're gonna like extend these guys to intersect here. Okay. And we're gonna draw this. And
I personally think that the most intuitive thing is to first drop this line between A and B, and then like use right angle to motivate thing. But
yeah, you can like note that this guy is cyclic because like these guys are equal, right? And AOD is 90 degrees by definition, so ABD is 90. Boom. Yeah, I think it's more natural to start with that, and I actually think we might want to edit the solution to like be in that order. But anyway. ABDO is cyclic, so ABD is right? And then the idea is that like if you extend this, you end up getting that these guys are equal.
and this is because originally you had these isosceles triangles. AOB was isosceles, so you could, it's natural.
Yeah, you have like congruent things. Like alternatively, you can just like say A prime is a reflection of A across O. I think that's what the official solution does. And you're like, oh, hey, these guys are congruent. This guy's right. Oh, hey. And I actually think these steps are kind of orthogonal. Also, you don't actually need OCA, I think. But anyway, now O, because O is a midpoint of A prime, it's also a circumcenter of this potato, right? And then you get the like ODB is equal to OCA. I actually don't think you need the circumcenter at all. But like anyway, it's a midpoint, right? So like you have some BH half shenanigans. And you're like, oh wow, these guys have the equal. They're equal. Like this area is equal to this area. And this area is 9, this is x plus 9. And then you can do some area ratios. I'm not gonna type it up, but like I'm gonna copy it. But also this is P, that's like kind of hidden. But yeah, this is P. And again, this is like literally just BH half stuff. So basically you can like use these area ratios and eventually you get x over 9 that's not a good 9, is 14 over 2x plus 9. Because like
This is a good basic core idea in itself. I wouldn't say this would constitute a problem, but this is actually a pretty good basic idea that happens.
Yeah,
this
this-
ratio thing technically just follows from PowerPoint. It's like if you think about it, like this, if this is like a like fucking internet, Jesus Christ, it's not enjoy working. Okay, so like if this is okay, if this is A and this is B, this is C, this is D, right? Then like AD equals BC, and then if you treat each of these areas in this cyclic quadrilateral is going to be like, actually it doesn't even matter that they're cyclic, I think, because basically like each of these areas are going to be like AC, BC, CD, and BD times like 1/2 sine this angle or whatever, and when you basically take the product of these opposite areas, they should be equal. So like 14 times 9 plus x times 2x plus 9. So technically no PowerPoint required either. This is just like a thing that's true. It doesn't have. Yeah.
Wait, well that okay, no, the area thing is not PowerPoint. The length thing is a PowerPoint, but yeah.
Yeah. But the area thing, I'm pretty sure is just generally.
Yeah, it's generally true. It's just a what's it called? A consequence of half AB sine C.
Yeah.
Yeah, I think DJ Mathman had a problem on the Amy that like involved this. Like it was the full quad prop from 2021 too.
Like actually, I'm not even entirely sure you need like this reflection, this A prime guy at all.
Yeah,
I
think
guess
like
it helps for 2x plus 9.
I think you could do like drop an altitude here, and then that would like remedy the situation where you could find that this was 23 over 2 plus x, and then this thing is twice that, you know, and then you could find this expression, and then you solve the problem. But,
Yeah, something like that. Okay, yeah. This one is a lot of ways to solve. I want to briefly outline a slightly cursed solution. Let me see if I can actually pull it
You can
up.
make an extra slide at the end of the slides, like.
Can I copy this entire slide? No. Okay.
Copy the. Here, I'll just do it.
At the end of the slide. Yeah, you can just copy it. Yeah, there's a way to solve this with like exactly 0 IQ points. Like you could just do the problem with trigonometry. I will.
I mean, I actually tried to approach that yesterday with trigonometry, and like you could get into some pretty dangerous things like tangents and stuff if you're not careful.
Oh yeah, you can like do stupid stuff. But like if you bail out as soon as you decide not to be an idiot, or like if you bail out as soon as you start doing idiotic stuff, like trigonometry is pretty safe.
Hey, trigonometry is optimal. Like I'm very convinced that like people are just not good enough at trigonometry anymore. Everyone's either like like a huge like synthetic like I must angle chase and add and multiply only, or they're just like hardcore bashers that like can like solve cortex in their head or something. Like I just don't think there's an in between anymore, and I think that's bad because trig is so powerful.
Yeah, it's like one of the actual techniques that like work without being stupid. Okay. Well, this is getting annoying. So I'm just gonna copy this. That's actually the wrong problem statement. Yay. Are these diagrams gonna show up? Okay, there you are. So the idea is you can let the like large angle here be theta. And this here be theta. And essentially, like what you can do is like set the hypotenuse. Wow, this is like sine theta h. And wow, like this is also a thing, right? And you can like subtract this area and this area and do like some, I think, some half AB sine theta, like crap. And basically you can
I
win.
think we can use like ratios or something.
Yeah, ratios with half AB sine theta. Because you know this guy is 5, right? Do we? Is this guy 5?
Yeah, we do.
Yeah, this guy's 5, right? Um, and so essentially, you just like use
Wait,
half
we
AB
actually don't
sine
know
theta.
any lengths, right? Do we actually know any length?
No, do we know it's
5 is an
5?
area.
No, sorry,
Yeah.
we know this guy is 5. This guy is one that's 5. Like essentially, we can like pull some half AB sine theta stuff. Because this guy's isosceles as well.
I think your trick expression was a lot more complicated.
Yeah, I think it was like something like I'm gonna screenshot it because like I don't really want to write it. I think it was something like this. I honestly do not remember like what I did. Like this was two. No, this is a year and a half ago. But like I know there is a trig solution of this form.
Yeah, this might have been like before EMF.
Yeah, this is before EMF. I forgot how I did this. This is a really old problem. Okay, what the hell? It's not showing up.
Okay, I can just summarize an approach. There is something that happens to be true about theta. You can use theta. Basically, you can angle chase to find all the angles in terms of theta, the theta that Dennis has chosen here, and then you can express 14/9 as some function of theta, and this gives you a value for theta, which kills the problem.
Yeah, and there's some like sine stuff. Half AB sine C ratio shenanigan. Okay. Who's doing this one? Aaron?
Oh yeah, this problem. I just looked at it a little bit just right now, and this problem is concerning. Honestly, um, Arusha's Arusha's a madman for this. So you know how most problems have like two sections, or like one of them is the main idea, and the second one is using the main idea to like chop up the problem so you can actually like answer extract, right? So this problem is like those two parts, but there's also the part where like you don't really understand like um why the students have to work alone and deduce the 6 areas with their logical skills until like the end. Like you don't understand until the end why this is like a necessary part of the problem, which is can be scary. Um, so, anyways, this problem, the first part is distinctively about geometry, which is yes. So basically, if you label the areas like A, B, C, D, E, F, then you know stuff like A and D are opposites, and then stuff like B plus D plus F are like um so red, yellow, blue, the primary colors, or green, orange, purple, the secondary colors. Um, I'm using pigments by the way, but um, so basically what happens is if you move the point, and this is very similar to that DG Mathman um, troll problem back like 4 years back or something. Or like if you move the thing, the area is like invariant throughout certain numbers of triangles. So like orange plus green plus purple actually like stays the same as you move um, the middle point, and same thing with the other area. So you see that the total area of the entire hexagon is actually going to be twice that. So it's actually twice some integer value. So the area um, is going to be twice this. And actually, it's also 3 times this. So those are the two geometric observations that are like very powerful in forming like the initial main idea of the problem. And so this is why this question is geometry. But afterwards, I'll go through some things about some details about the answer and why you'll be less convinced it's geometry at the end. But right now, just know that this is like very geometric. That if you move the point around, then orange plus blue is going to stay the same. Like if you move the point here, orange plus blue is still going to be that large. And same thing with yellow and purple, and same thing with red plus green. So therefore, the area is going to be 3 times something, but also 2 times something. So it's going to be 6 times something. So that really actually reduces a lot of the problems, a lot of the things in the problem. Obviously, you still have to deal with a lot of stuff, but so basically, what happens is when Arush designed this problem, and I have to admit this problem is very bound to the aesthetics, which is like very unique to this problem. But hey, it's Matt's 2023 aesthetics. So basically, what Arush does is he does casework on A plus D, and A plus D is also equal to A plus D is the same thing as B plus C, and I'm sorry, B plus E and what's it called? C plus F. So these things are all equal. And what's nice about this is that they are equal to an even number because you already have the factor of 3, but you still have a factor of 2 here. So he just does casework on what A plus D equals B plus E equals C plus F can be equal to. And if you list the numbers from 1 through 9, I'm just gonna do that because why not? You can like start to test out which even numbers can be worked. So if A plus D was equal to 4, then 1, 3 would be the only combination. So that's obviously a failure. So you would need 3 like distinct combinations for this. So 6 would be 1, 5, and 2, 4. So that's not good. And then 8, you would have 1, 7, and 2, 6, and 3, 5. So the minimum is 8. So, and symmetrically, you can see that since 10, since 5 is like the average of all the numbers, then 10 is going to be the average of the sum of 2 numbers. So you can see that 14 doesn't work. You can check that yourself. 14 is not a possibility. So 8, 10, and 12 are the possibilities. So basically what happens is you do for each of these cases a pairing of numbers, and you can like select for which ones are going to be that satisfy the other condition. Like basically the 2 geometric conditions that become algebra are the conditions that you're like caseworking to like get around. So for example, if we were to do B plus D plus F matching on 8, we would have 1 1, 7. You're going to see this in a little bit. Obviously Jamboard requires you to click down first, but 1, 7, 2, 6, 3, 5. And so basically you're selecting one number in each of the 3 pairs, and you want them to add up to 3/2 times 8, which is 12. So the way you would do that is you would select 1, for example, because 1 has to be in one of the combinations, and then you have 11. So that's obviously going to have to be 6 and 5. So there's one way to do this, and so basically 1, 7, 2, 6, 3, 5 is a single solution to this thing, and you can imagine how that would fit on this grid. It doesn't really matter the order, but the intention of the problem was that the students would not be able to figure out the thing up to order, up to the permutations of the areas. So that's that. And then you have 12, which, as you can expect from symmetry across 20, if you have enough insight about that, you'll see that like 3, 9, 4, 8, and 5, 7. If you're going to sum to 18 from these things, that's going to look something like, okay, if you pick 9 first, and I should probably note that like these are these 8, 10, and 12 are the 2 sums, and then 12, 15, and 18 are the 3 sums. That's how we're going to associate the cases. Oh shoot, I have the problem that we have had. Okay, so in this case, 9 associates for 18, and that would be a sum of 9 for the other ones, and that involved this and this. So 9, 4, and 5, and 3 and 7, this is the only solution. So each of these 2 cases came out cleanly, and then we're going to check 10. 10 is a little bit more annoying. I'm going to erase some space for that. But basically 10, there are 4 pairs because 1, 9, and then all the way to 4, 6. So you're going to have to like check the cases of whether certain things are in or not. So I can list this out right here because you deserve to see this. But basically, what Arush said is basically if 1 and 9 has like an entry to this thing, then like you would have to have 9 and then 2 other numbers that sum to 6. So that would have to be 2 and 4. So that is certainly a solution. And in this case, you're totally ignoring 3 and 7. So you would have 1, 9, 2, 8, 4, 6 is the solution. And then the other one is if you do not have 1, 9, and because this is the only one that involves 9. So assuming you don't have 9, you have 2, 8, 3, 7, 4, 6. And in order to find a sum of 15, so again, we want the 15 because that's 3/2 times 10. If we want 15 from the bottom 3, then we're going to get it from like 7, right? So 7, and then 2 things that sum to 8. So 2 and 6. That's the only way. So the bottom 3 also form a valid pair. So 2, 8, 3, 7, 4, 6. At this point, you're probably wondering, I've done so much on trying to solve this problem. Why is there still this intensely logical thing about the students each having one of the numbers and not being able to deduce all the other things? So what exactly does that mean? So we have the 4 solutions. Here on the left we have 2, and here we have the other 2, 1 and 2. So basically these are the sets of 6 numbers that could possibly work, and basically none of the students can determine a unique one. So like the students are given one of the other 3 numbers. So if one of the other 3 numbers is like shared between at least 2 of these 4 possibilities, then they would not be able to deduce them. So in that case, the 3 numbers that would not allow like deducing is, I think, 1, 5, and 9. I'm actually reading off of Rush's solution. This part is actually hard to explain, but the logic thing has been a part of like advanced AME problems, even like see 2021 AME 2 number 11. there's some total thing that's based on logic, and it just complicated. So that's like complicated enough. So this problem is I would say a bit over the top, but I think it's held very well by aesthetics. So that's why we all gave it a pass and let this special problem appear.
Yeah, the idea behind determining whether, like, let's say I tell you, like, we look at these four solutions, right? And let's say I tell you that the digit 2 is not part of our solution, like our 6 areas. Well, you look at these four solutions and you're like, huh, which one of these has no 2? Um, this one. Wow. And now I can uniquely determine it. So that's like bad. And if you check, you're like, oh, hey, each of these digits is in 3 of these solutions. So if I tell you it's not there, I know which solution we're working in, except for the digits 1, 5, and 9. So that's like the idea.
Yeah, so it's actually not like what appears twice versus what appears once, but instead what appears twice versus what appears thrice. Because what appears thrice is easily deducible, and what appears twice is ambiguous.
Yeah, you can also like consider, hey, I'm telling you an element in the complement of these sets, right? Like if you just consider this solution, consider like 1, 2, 6, i.e. the digits not in the solution. Right?
Then like what Aaron was saying earlier about like the statement is really like clean. Like a thing with Irish's problems where if you look at first tiebreaker problem from last year, like the statement is very surprising. In fact, there's only there's a unique answer. It's like it was about like arranging operations within 3 digits. Yeah, it was very surprising that there's a unique answer, and it's the same thing again here. Like numbers used in the problem besides digits and stuff. So just a really clean statement, and that's what makes Irish's problems really nice. Like from both the problem solving and aesthetic point of view.
Also like this one. This one is so good. Like it's just, hi, here you have like 2 triangles. And there's like a very simple configuration, but it's also really rich, which is like kind of impressive.
Yeah, I think like problems should aim to be like you have minimal elements, but like a really complicated like result, rather than like a complicated, but like it's not a very deep idea or something like that.
Yeah, this is a
Yeah,
really
this is actually like true for like all of Rush's problem, even the one I just told you about. But they're all like very compact ideas. Like I think earlier in Matt's, like Matt 1, I wrote this problem with someone else that was kind of over. I think number 6 was kind of overboard in like computation or something. So I think that's improved.
Yeah, we
Yeah.
were debating a lot like about how to order the P3s and stuff, in particular because like 9, like at least when I saw the when Ethan explained the idea of P9 to me, I was like, or when Ethan and Aaron, one of them, explaining the idea of P9 to me, I was really impressed by like the residue system idea. So like that deep mathematical idea like made us want it at 9, but also like Irish's statement seems like a final kind of statement because of its like I don't know, like its elegance and stuff like that. So yeah, that's what we're debating internally.
I think tiebreakers are usually like the weirder problem statements. This one's a pretty weird problem statement. So I think like, yeah, I think this problem statement gets away partially because it's like on tiebreakers. Like it's a really, really non-standard problem. Like what the heck is this, right? Like you look at it like, what the heck am I supposed to do with this? Like, huh? And like even the solution is like, so you have like a bunch of random, almost like random seeming disjoint observations. It's like,
Like even like the geo observation, it's like really like this feels like a complete combo problem, and then you realize there's like a geo like you need a geo observation to start, and it's kind of weird.
yeah. Okay, I think we're about done. I don't know. People can feel free like after stream to talk just about tiebreaker formats because
Well,
like
hopefully we can like compile the solutions because that's always troublesome.
yeah, I think our solutions like we're gonna have to internally do some editing. I took a look at some things of like, and then we said some things, and there's also some missing alternative solutions like the trig thing, because no one actually understands the trig thing completely anymore. I think so. Like we actually need to look at it and figure out what the hell is going on. Because like I just know it's possible to do some weird thing. I don't know what's actually the solution because I wrote it up really poorly, like in 2021. So I don't know. Or is it 2022? Something like that. But yeah. Anyway, thanks for sticking around. I think we're gonna end the stream here. Yeah, that's it.